Thank you very much for joining us today. We've got Dr. Wei Jin Wang, Principal Scientist at Queensland Department of Environment and Science, who will be presenting on the topic of enhanced efficiency nitrogen fertilisers, potential benefits and selection of products for sugarcane. The webinar will consist of presentation for around 45 minutes and we'll follow that by a Q&A session of around about 15 minutes. And during the presentation, as I'm sure you're all very familiar with, if you can just make sure that your microphones are on mute. However, if you'd like to type in a question during the presentation, feel free to just put that in the chat function at any time. And if you don't know where that is, there's a little speech bubble icon at the top of your screen. So if you just open that, you'll be able to see the chat then on the right-hand side. So Wei Jin may answer your question at the time as it appears, or he may wait until the Q&A, and I'll go back and read through those to make sure we capture everyone's questions. And then during the Q&A, again, you can either type a question into the chat, or you can raise your hand using the little hand button also located at the top, and I'll go through and sort of call on people who I can see have raised their hands. And then just towards the end of the webinar, I'll put a link into the chat to a survey, and it would take you about 2 minutes if you're able to take the time to complete that. It's very helpful to us to understand how useful you found this webinar, so that we can understand a little bit more about what SRA can do to provide support to industry. So just a little bit further on this project, it was supported by funding from the Australian Government Department of Agriculture, Water and the Environment as part of its Rural R&D for Profit program, Sugar Research Australia, and then we also had financial contributions from ICL Specialty Fertilisers, Incitec Pivot, Herbert Cane Productivity Services Limited and Pharmacist. Now, I'd like to hand over to Dr. Gus Manatza, one of the managers of research missions at SRA, who will provide a little bit more information and introduce Dr. Wang.
Well, thank you, Alison. I hope everyone can hear me. Thank you for joining us so early. So we only have about an hour to go through this one, so I'm just going to be quick. As Alison has alluded, this project is one of 3 projects that SRA invested on behalf of the sugarcane industry to look more into how can we make more money from nitrogen with a focus on enhancing the nutrients use efficiency of intensive cropping and pasture systems. So this was part of the Department of Agriculture, Water and Environment, Rural R&D for Profit program. So the Federal Department of Agriculture was the main funding, with co-funding or in partnership with the Cotton Research and Development on behalf of the cotton industry, Dairy Australia, and Horticulture Innovation, and of course SRA. So as SRA, we invested in 3 sub-projects under that program, of which Dr. Wei Jin led one of them. The other one, we did a seminar sometime last year, which looked at improved nitrogen use efficiency through accounting for deeper soil mineralizable N supply and deployment of enhanced efficient fertilizers and crop demand. This was led by the New South Wales DPI and in partnership with Sunshine Sugar at Southern Cross University. The other one is still ongoing, which is led by the Queensland government researcher, and this is looking at new technologies and management for transforming nitrogen use efficiency in cane production. So once that they're still doing the final information gathering and data, once that is done, maybe we'll organize another webinar. But today we're focusing on what Dr. Wei Jin did and some of the key findings. If there's anything that we're going to take away from this one, I hope, is that how does a farmer at a local level make a decision on whether they should use these enhanced efficient fertilizers, which are usually loosely called slow release fertilizers. and what are the economic costs, what are some of the major considerations before we make that final decision. Dr. Wang has led several projects in the last 20 years on soil carbon and nitrogen cycling and management, including carbon sequestration, nitrous oxide emission mitigation. In particular, he has been collaborating with various research, development, and extension organizations in investigating practical farm management strategies to increase fertilizer, nitrogen use efficiency, and minimize nitrogen losses into the environment, which is a big issue for us in the sugarcane industry. So without taking too much time, I will encourage people to pop in your questions in the chat so that we don't interrupt the presentation, and then we have some time for Q&A after the presentation. So over to you, Dr. Wang.
Thank you very much, Alison and Gus, and thank you very much for the opportunity for me to communicate the results from the project to the community as well. But let me upload my presentation. Can you see it?
Yes, it's in presentation mode now, so that's great.
Oh, sorry. I need to go back to the first slide, perhaps. How about now?
Yes, that looks good. Yeah.
Good morning, everyone, and thank you for making your time available for today's webinar on enhanced efficiency nitrogen fertilizers. Let's call it EEFs. Today, I will focus on the potential agronomic, environmental, and economic benefits of EEFs and how we should select different products for your farm. First, I would like to thank my wonderful colleagues and collaborators from several R&D organizations, including DES, that's where I work in, HCPSL, TRAP, based in Italy, staff at Vanderbilt, and the pharmacist team at Mackay. In the next 40 to 50 minutes, I will touch on several key questions. Why are we interested in EEFs? And are all EEFs similar things? Can EEFs improve nitrogen use efficiency, yield, and farming profit? Can EEFs maintain yield at lower rates than normal urea? Can EEFs offer any environmental benefits, such as reducing emissions of nitrous oxide, which is a very potent greenhouse gas and the #1 depleter of ozone in the atmosphere? And can it reduce nitrate leaching into groundwater? If so, can environmental credits be used to offset the extra cost of EEFs? And finally, how to choose the right fertilizer based on site and weather conditions. First, I would like to go through a simplified diagram of nitrogen cycling processes in soil to help those who are not familiar with the nitrogen loss pathways to understand my talk. Basically, once urea is applied into soil, it can be converted into ammonium within a few days through a hydrolysis process that is performed by an enzyme called urease. Urea hydrolysis not only generates ammonium, but also increases soil pH. When ammonium exists in alkaline conditions, of course, it forms ammonia that can be easily lost into the air through volatilization. That is why growers should bury urea into the ground if possible to minimize ammonia volatilization. For the ammonium that stays in the soil, it can be converted to nitrate through a process called nitrification. And it is nitrate that makes trouble indeed, because under wet conditions, either after heavy rainfall or after excessive irrigation, nitrate can be leached out into the groundwater or run off into surface water, and also it could be lost as gases through a process known as denitrification. And as said, one of the gas is nitrous oxide, which is a strong greenhouse gas. Indeed, based on the isotopic tracing studies in the past, only about 20 to 40% of fertilizer nitrogen can be used by crops, with approximately 20 to 40% remains in the soil at the end of the cropping season. What concerns us is that about 40 to 60% of the fertilizer nitrogen is generally lost from the farms, which not only causes economic loss, but also leads to environmental problems. So why on earth does so much fertilizer nitrogen get lost from the system? Well, many factors can cause nitrogen losses, and one and a few of them may dominate at a specific site or at a given time, depending on the situation. For sugarcane, particularly routine crops, we normally apply fertilizer as urea shortly before the wet season. Because urea is very soluble, it can be converted to ammonium and nitrate quickly, as I have just showed in a previous slide. Because the young crops do not take so much nitrogen at the early stage, so the nitrate builds up in soil. When we get into the wet season, the nitrate can be easily washed away or be converted to gases by soil microbes, as I just mentioned. There are a number of techniques that can be used to enhance nitrogen use efficiency and minimize nitrogen loss, including the 4R principle or 6R principle, in my opinion, which some of you may have heard about or are even practicing. That is right rate, right time, right frequency, or right placement of nitrogen. Placement means, as I just mentioned, you should not place urea on the soil surface and should bury. And right frequency. We should also consider the right management practices, such as using the right variety and right irrigation techniques, for example. In addition, we should choose the right fertilizer or fertilizer type or formulations, including the use of Eefs. And this is what my presentation will focus on today. So Eefs are designed to restrict mineral nitrogen, particularly nitrate accumulation in the early season by blocking urea hydrolysis or the conversion of ammonium to nitrate, or by slowing down nitrogen release at the early stage and extending mineral nitrogen supply for longer periods, so better matching crop nitrogen uptake. There are various EF products in the market, which can be classified into a few types, including urease inhibitor, such as the green urea NV with the NBPT as a urease inhibitor, and nitrification inhibitor coated urea, for example, uptake, double inhibitors using both urease inhibitor and the nitrification inhibitor. Another type is slow or controlled release fertilizer, including less soluble compounds like urea formaldehyde or sulfur-coated urea or wax-coated urea or other fertilizers, which are not really commonly seen in today's market. And the most common product is a polymer-coated urea or controlled release fertilizer or urea. Now, there are increasing concerns with possible pollution of microplastics with polymer-coated urea. And I think there is a trend for the industry to move to the biodegradable polymers to minimize or reduce avoid microplastic pollution. Here is a comprehensive analysis of worldwide studies evaluating 4 major types of EFs. Polymer-coated fertilizers, they call it a PCF, nitrification inhibitor, NI, urease inhibitor, UI, and double inhibitor, with both urease and nitrification inhibitors. The blue dots show yield increase of about 4% on average in upland farming with NI, UM, and DI, but with no significant yield benefits with the PCF. For paddy rice, EFs increased yield by 5 to 10% on average. The bottom bar show nitrogen losses through ammonia volatilization or nitrate leaching and runoff in dryland and paddy rice systems. In terms of soil moisture or wetness, sugarcane farms should be somewhere between the 2 types of systems. These are broad averages. And these products generate any yield and environmental benefits for cane crops in Australia? This question has prompted a few research projects on cane, including the More Profit from Nitrogen project. In this project, we set up 6 field trials from Innisfail to Bundaberg over 3 cropping seasons from 2016 to 19. The sites covered a wide range of soil properties, including different soil types, clay contents, total organic carbon content, and mean annual precipitation. Each field trial consisted of 12 treatments to compare different fertilizer formulations. Urea, nitrification inhibitor-coated urea, and PCU with 3 blending ratios with urea at 25%, 50%, and 75%. We also tested these fertilizers at 2 different rates, 6 ES and 75% of the 6 ES rate. For urea, we use 125% 6 ES rate was included to see if high nitrogen rate would benefit yield. On top of these fertilizer treatments, an unfertilizer treatment was used. All the fertilizers were band applied at about 10 centimeters below the ground. In addition, the soils were tested before the fertilization, and if any nutrient other than nitrogen, such as phosphorus or potassium, was found deficient, fertilizer containing that nutrient was applied. We assessed Eefs against normal urea by looking into nitrogen release dynamics from PCU in relation to crop nitrogen uptakes, ammonium and nitrate accumulation in soil applied with the EF versus urea, and the downward movement or leaching of soil mineral nitrogen, particularly nitrate, crop nitrogen uptake and nitrogen use efficiency, cane sugar yield, of course, and profitability. At some sites, we measured nitrous oxide emissions as well. So at the end, I will present some nitrous oxide emissions data, but we didn't measure that at all sites. First, let's have a look at a field incubation study in which we measured the nitrogen release dynamics from PCU products. This will allow us to see how well PCU nitrogen release would match crop nitrogen uptake. The method we used was pretty simple, but served for the purpose very well. First, we placed PCU granules into the mesh bags and then buried them at about 10 centimeters below the soil surface. Later on, we sampled fortnightly, monthly, and then bi-monthly. And the nitrogen release was estimated from weight loss, which was first calibrated against nitrogen loss. Here are the results from the mesh bag studies in the 2017-18 cropping season. What surprised us is that the PCU nitrogen release dynamics were very similar among different sites. This was in spite of the substantial differences in the soil properties and in rainfall at different sites. So it is clear that the PCU nitrogen release was not affected much by soil properties and rainfall. At least the soil were very dry, I think. We know temperature is a regulating factor to nitrogen release from PCU products based on previous studies. As expected, the cumulative temperature differed at different sites. However, if we look into the graphs closely, we can see that about 80% of the PCU nitrogen release occurred in the first 4 months. And during this period, the cumulative temperatures were not substantially different among the different sites, spreading from Eefs to Bundaberg. So this explains why the PCU nitrogen release dynamics did not differ significantly at different sites. Indeed, the cumulative nitrogen release from PCU can be predicted accurately with time only, as with degree days. For those who do not like mathematical models, we can draw 2 straight lines for the first 2 months, and then after 3 months. For the slopes of these, from the slopes of these lines, we can see about 1% of the fertilizer nitrogen was released per day in the first 2 months after application. And after about 3 months, the nitrogen release rate dropped to about 1/10 of the percentage per day. Subsequently, we further tested with 4 different PCU products in the 2018-19 season to verify what we observed with that single product before. This time, we included Master with a 3-month release, AgroMaster Standard with a 3-month release, and AgroMaster Tropical, which is a 4-month release product made in 2017, and another AgroMaster Tropical with a 4-month release made in 2018. Each fertilizer was incubated at 3 different sites, and the results confirmed that nitrogen release dynamics from all these PCUs did not differ significantly at the different sites tested. This is really great because it means the amount of nitrogen supply from a specific PCU to crop can be predicted accurately with time, with no complication from variations in soil and weather conditions, which is almost impossible with normal urea. Here, all the nitrogen release curves were placed together to help compare. We can see Master and AgroMaster Standard. Both were labeled as 3-month released products, had very similar nitrogen release dynamics. The 2017 AgroMaster Tropical behaved almost identically in both years. However, the 2018 AgroMaster had a nitrogen release pattern between the 3-month products and the 4-month product manufactured in the previous year. Perhaps due to some labeling errors, I reckon it should be labeled as a 3.5-month release. Now, a bigger question is, which product should I use? Well, the answer is can be simple. We should choose the one that best matches crop nitrogen requirements. So let's first have a look at the dynamics of crop nitrogen uptake from the fully nitrogen fertilized plots on the top and from the unfertilized plots at the bottom. For the fertilized crops, nitrogen uptake were much higher at Bundaberg because that site was irrigated. At the unfertilized, for the unfertilized crops, the crop nitrogen uptakes differed substantially, suggesting the soils had different nitrogen supplying capacity. As expected, the fertilizer crops had much higher nitrogen uptakes than the unfertilized crops during the first 6 months. Here, I placed the crop nitrogen uptake dynamics in the fully fertilized and the unfertilized treatments in the same graph for each site. The difference between the fertilized and the unfertilized treatments would be crop nitrogen uptake from fertilizer nitrogen. Or in other words, the amount of fertilizer nitrogen required by the crops. We can draw a line for the dynamic changes in the height of the shaded area to show fertilizer nitrogen requirement changes with time, like this. From these curves, we can see that the crops no longer needed fertilizer nitrogen after about 200 days at Bundaberg and after about 180 days at Eefs, about 180 days at Eefs. While at Mackay, the crops continued taking up fertilizer nitrogen in the later cropping season, but at a very slow rate. For a fertilizer nitrogen supply from the 3 PCU products at the 60 ES rate were much higher than the crop nitrogen demand. It shows how much more nitrogen we usually apply than what is required by the crops. So there is a great potential to improve nitrogen use efficiency. However, with the current management practices, we have to apply much more nitrogen than required by the crops, because some can be lost and some remains in soil, as I showed in a previous slide. After taking into account fertilizer nitrogen use efficiency, that is the percentage of fertilizer nitrogen taken up by crops as measured using urea, because no data are available with PCU. Here are the plant usable nitrogen from the 3 different PCU products in relation to the fertilizer nitrogen demand by the crops. From these graphs, we can see the nitrogen release from the 3 months release AgroMaster standard substantially exceeded sugarcane crop nitrogen uptake during the early season, which may pose a risk of nitrogen loss following high rainfall in the summer. If we look into the graphs in detail, If we have a look at the graphs in detail, we can see the 4 months release fertilizer tend to undersupply nitrogen at Bundaberg. And even at Mackay and Innisfail, the nitrogen release from the 4 months product tend to be slower than the crop nitrogen, assuming the nitrogen use efficiency we use was correct. And for the 3.5 month release product, and it seems it is somewhere between the 3 months, 4 months, and it seems it matches crop nitrogen pretty well. We do need a little bit of surplus of nitrogen, but we don't want too much surplus nitrogen at a given time, so that we make sure there would be enough nitrogen available for the crop. So it seems to me the 3.5 month product is better than the 3 months and 4 months release product. Now, a big question is, can the better synchronized nitrogen supply from PCU really increase crop nitrogen uptake and yield? Here is what we observed at Ying'an as an example. First, let's have a look at the nitrogen uptake and yield in response to different rates of urea. These 3 treatments. So increasing nitrogen by 25% from 6 ES rate, this one, did not have any yield benefit at the 6 ES rate. That's a bright colored bars. The 50% and 70% of PCU blend increased the nitrogen uptake, but not yield. And no yield responses to the other EF2 compared to normal urea. At the 75% 6 ES rate, that's the pale colored bars. these ones. Again, the 50% and 75% PCU blend and N-tech maintained crop uptake compared to the normal practice with urea at 60 ES rate. But the EF at 70%, 75% 60 ES rate decreased sugar yield by about 1 ton per hectare. That's like this.
Sorry to interrupt, Wei-Jin. I'm not sure that. Are you using a pointer? Because I can't quite see it, but it could be me.
Oh yes, I did.
I saw it in earlier. I saw the red, but it seems to have gone again. Unless.
How about now? No.
No.
About
oh
now?
yes, now I
can.
can.
I need
yes.
to go. Sorry.
That's all right.
I need to go to the top screen. Yes, thanks for reminding.
That's all right.
Where are we? So the EF did not result in yield increase and failed to maintain the sugar yield at the reduced nitrogen rate compared to normal urea at the 60 ES rate. I should point out that the yield responses to EFs at each site is different from others, and even the results at the same site can vary significantly between different years. I won't show the results from all sites in each year one by one because of the time. Instead, these scatter plots show the relative sugar yield between normal urea and each EF product. The diagonal line is a one-to-one line, not a regression line. The points above the one-to-one line represent positive yield responses to EF, and those below the one-to-one line represent negative responses. So the yield responses varied with sites and with seasons at the same time, regardless which EF we tested, whether it's PC 50% PCU or 75% PCU, 25% or an ICU. At the lower than 60 ES rate, both positive and negative responses were recorded as well. Now, I guess someone would question, you observed a nice synchronization between PCU nitrogen supply and crop nitrogen uptake. Why did that sometimes fail to lead to better yield? Well, this is a big question indeed, but I think there are a number of reasons for the lack of yield benefits from using EFs at some sites or in some seasons. For example, if we can't see the yield, for example, high nitrogen supply from soil nitrogen, or the nitrogen is less limiting because of high nitrogen mineralization from soil organic matter or from chemtrails, or sufficient nitrogen supply from fallow legume crop rotation, or you got residual fertilizer nitrogen from the previous season. Or we have overly used fertilizer nitrogen. It means whether you use normal urea or EF, you got enough nitrogen anyway. And if there is a low risk of nitrogen loss, EFs would not perform better. And perhaps there are other limiting factors like macronutrients or soil physical chemical constraints, or inappropriate management practices, like you applied fertilizer at the wrong time, you put it on the soil surface, or we got pests. And adverse weather conditions could also be a contributor, like a drought or water logging or flooding, which we experienced all of them. And when such adverse weather conditions exist, basically the fertilizer nitrogen, regardless of what they are, would not perform well. And perhaps we have modest nitrogen demand during the mid to late season. Therefore, prolonged nitrogen supply from PCU may not benefit much, which is a big question. And maybe we have a spatial variability. As you know, sugarcane is a big crop, and the soils and the sites quite often, and even the crops are not uniform. Therefore, they can cause experimental errors. And even the operators of the experiments may have artificial errors, like the inaccuracy of weighing bin or sort of biased plant sampling that can all cause lack of responses to EF. In other words, if EFs would not perform well under these conditions, under these conditions, EFs would not perform well and therefore are not recommended. Next, let's have a look at the environmental benefits of EFs, for which I'm much more optimistic. This slide shows soil mineral nitrogen dynamics in the top 20 centimeter soil at two sites near Ying'an over 3 seasons. The reddish colored lines are those with PCU blends. As you can see, much higher mineral nitrogen contents were maintained in mid to later cropping season compared to the gray colored urea treatment. In contrast, soil mineral nitrogen in the normal urea, these ones, in the normal urea treatment, or even the green colored NICU treatments, dropped to very low levels, about 3 to 4 months after fertilizer application, which signaled perhaps rapid and substantial loss of urea nitrogen. If we have a look at nitrate nitrogen movement into deep soil at Bandebra and Ying'an, the black colored or gray colored normal urea treatment had more nitrogen leached to deep soil than EFs. Here is an example to show how fertilizer formulations affected nitrous oxide emissions. As mentioned before, nitrous oxide is a very strong greenhouse gas and the predominant ozone depleter in the atmosphere. And high nitrous oxide emissions are often an indication of high gaseous nitrogen loss. Here we tested nitrous oxide loss at the recommended nitrogen rate and the suboptimal nitrogen rate and excessive nitrogen application rate. As you can see from here at the with the normal urea, as nitrogen rate increased from 112 kilogram nitrogen to 160 to 208, nitrous oxide also increased with the nitrogen application rate. And the PCU actually slightly increased the nitrous oxide emissions compared to the normal urea at the same nitrogen rate, which shows perhaps because the PCU maintain the nitrogen in soil for longer time, therefore supplied more substrate for nitrous oxide production. But with the NiCO, much lower nitrous oxide emissions were recorded. In other words, NiCO was very efficient in reducing nitrous oxide emissions from soil. And we put all the results we observed in the past years in this scatter plot again. It's amazingly nitrification inhibitor reduced the nitrous oxide emissions consistently, regardless of the site conditions or weather conditions. Sometimes we got more reduction, sometimes we got less, but it's always lower than normal urea treatment. But PCU did not always decrease nitrous oxide emissions, and sometimes even increased the emissions as compared to normal urea. This is partly because PCU retained more fertilizer nitrogen in soil for longer time, as I just mentioned, and thus providing more substrate for nitrous oxide production in soil. Someone may ask, can the above environmental benefit of Eefs be translated into economic benefits? I think it is possible. Apart from yield increase, this would depend on policies and prices in the environmental initiatives, such as the Emission Reduction Fund, Reef Nitrogen Credit, and the Land Restoration Fund, for example. First, let's have a look at the fertilizer costs. Assuming the fertilizer price is $500 per ton for urea, $620 per ton for NiCO, and $800 per ton for 50% PCU blend, and the nitrogen application rate of 140 kilogram nitrogen per hectare. Using Eefs with a cost extra $37 for NiCO and $100 per hectare for PCU blend. Assuming a carbon price of $16 per ton CO2 equivalent for nitrous oxide emissions reduction, and a reef nitrogen price of $1.1 per kilogram nitrogen, which is the urea price, because it's not available yet, but should be higher than that, in my opinion. Let's use the fertilizer price in this analysis. It is possible to offset the extra cost for NiCO with the environmental credits, but to fully offset the extra cost of PCU, which we would need to partly rely on yield increase or price reduction. To summarize what I have just said, the duration of nitrogen supplies was certainly longer with the PCU than normal urea and NiCO. Nitrogen release dynamics from PCU varied little between different sites, which is great. It means the nitrogen release can be accurately predicted. And we got a better synchronization between PCU nitrogen release and the crop nitrogen uptake. Nitrogen leaching risk is certainly great with normal urea, or which may be slightly lower with NiCO, but least with PCU if the site got a lot of rainfall or good drainage. Nitrous oxide emissions is much lower with NiCu than normal urea, but there is an inconsistent trend between normal urea and the PCU. Sometimes PCU can reduce, sometimes can increase nitrous oxide emissions, as I explained previously. Yield responses to Eefs and thus profitability varied with site and weather conditions. Eefs are more suitable for farms with high nitrogen loss risks and no other constraints than nitrogen. And environmental credits may potentially offset part or all extra costs of Eefs. In terms of knowledge gap, we needed to do more work for better identification and prediction of key factors affecting yield responses to different Eef formulations. I think I don't have much time now, but before I finish, I just quickly show you that we developed a decision support tool to help select of PCU products or different different Eef products and normal urea. The decision tree is pretty simple, consists a number of questions and the yes and no answers. By using the decision trees, I hope you will find it's easier to select the right products for your farm. I will not go through the decision tree in detail. For anyone interested in it, please have a look. And quite importantly, I suggest visiting our final report, which is available in the SRA e-library, because in the report we have detailed explanation why you choose one product against others. I think we still have 6 minutes. That's all from me for today. For those who are still there, thank you for your patience and for listening. It is a pretty lengthy presentation. I think in the next 5 minutes or so, I'm happy to pick up some questions. Thank you.
Thank you. Thank you very much, Wei-Jin. And we'll go to the questions in a moment. I did just put in the chat the link to the final report that Wei-Jin mentioned. So it's on the SRA e-library and the link's in the chat. So if anyone has any issues accessing that, let me know. There were a few questions that came in during the chat, so I might go to those unless, well, but if you have one that you'd like to ask out loud, just put your hand up using that hand function. So Wei-Jin, the first one was in relation to quite an earlier slide. It said, this was from Bronwyn, would the timing of application influence the product choice? That is early application versus late season application.
Certainly. Let's have a look at the, can you see? Yeah, for the decision tree, we took into account of the early season or later season, but we did not specifically use those words. The reason is that we just tried to make the decision tool as simple as possible. Why the early and the later season would matter is because of the rainfall. So if you got early harvest, you all got a plant can, normally soon after fertilizer application, you got less risk of high rainfall. While if you go to a late harvest crop, and the risk of high rainfall, the possibility of high rainfall is much higher after fertilizer application. So we put some questions on rainfall, whether you like a question 3, whether you will expect rainfall or excessive irrigation after in the first 2 to 3 months after fertilization, instead of separating them into early crop or later crop. So it will be based on rainfall.
Thank you. Now there is a question about what was the method used to estimate the nitrogen uptake by crop, and I'm wondering, is that addressed in the final report, or do you...
Yeah, it is described in detail in the final report. Just briefly, what we did is we took plant samples from the plots, and then we just cut the plants into small pieces, dried them, and ground them into very fine powder, and then we analyze the nitrogen contents in the plants in the laboratory. And based on the biomass amount and the nitrogen contents, we calculate how much nitrogen is taken up by the crops at different stages. And because of the crop age, we use different sampling techniques, and the details are given in the final report.
Thank you. Now there's another one from Owen. Is the PCU in the high nitrous oxide release a 25-75 blend with urea? Again,
can you say it again, Alison?
Yes, sorry. Is the PCU in the high nitrous oxide release a 25-75 blend with urea?
For that one, we didn't measure. You know, we can only measure 6 treatments in each trial because of the limited number of automatic gas sampling chambers we have. But it's a very good question. Basically, if we see high emissions from those blend with PCU compared to pure and normal urea, the difference, the extra amount of nitrous oxide released would be because of PCU. So we can, if we observe the higher nitrous oxide emissions from one PCU blend, we would also expect higher emissions from other blending ratios. Maybe, you know, at a lower blending ratio, we may see less increase. Maybe I should point out that increased nitrous oxide emissions under PCU are not always observed. Sometimes we do see reduced or decreased nitrous oxide emissions. So it's really depending on a number of factors, including the site conditions and the weather conditions, and what time you received high rainfall, and what's the amount of rainfall you received at that time. So a number of factors affecting the effect of PCU or PCU blend on nitrous oxide emissions.
All right, thank you. Now we are just on 10 o'clock, so I'll just, I think there was only one more, maybe 2 more, but maybe we'll just have time for one. Harry said 6 easy steps has 6 easy steps has 6 steps. Did step 5 identify any nutrient constraints from other elements? Maybe that's not something you've really...
Yeah, it's a very good question. Yeah, I'm sure there is a step that that suggests we should identify nutrient deficiency from other nutrients than nitrogen, whether it's a phosphorus or potassium. But I'm not really sure whether it's a step 5 or not. Certainly, I'm quite sure there is a step to identify nutrient deficiency. And if you find other nutrients are deficient, we should apply them as a fertilizer. Otherwise, that would be the limiting factor to yield. Regardless how much nitrogen you apply, you won't get any significant yield benefit if there is other nutrients that are limiting crop yield.
Look, we've still got 60 people on the line. There are a couple of other questions, but I'm
Thanks everyone.
No. There's obviously a great deal of interest in it. So, we might just continue for maybe just 2 or 3 more minutes and see if we can whiz through the last few questions. So the next one was, considering nitrogen high volatilization and loss, should we be aiming for a better reticular system? Sorry, that's an unusual word, that can minimize N loss.
Reticular system.
The
volatile, I suppose, it's a very good question. Thank you very much. The volatilization, I guess you are referring to ammonia volatilization, which happens normally with normal urea. As I showed in one of the slides, when you put urea onto the soil surface, and then you got a lot of ammonium produced, and also with increases in soil pH. So under alkaline conditions, you got a lot of ammonia volatilization if you put the fertilizer on the soil surface. What we suggest is you should always bury the urea into the ground, like at least 5 centimeter deep, best 10 centimeter deep, and close the fertilizer slit or compact the fertilizer slit to make sure the urea is sealed in the fertilizer band. So that way, normally we can reduce ammonia volatilization to very minimal level. So that would not be a problem. So if you have problems with burying fertilizer into the ground, whether it's because of the lack of farming machine, or the machine is broken, or because of hard ground or rocky ground, or a lot of contrast, if you have difficulty to bury urea into the ground, you should apply urea before irrigation, or try to apply urea before rainfall. Although the rainfall forecast may not be always reliable, but it would be good if you can apply urea before rainfall or irrigation. That should minimize ammonia volatilization.
Thank you, Wei-Jin. Do you think genotypes differently respond to EEFs?
Genotypes, I don't think, it's an interesting question. I don't think we have any data at this stage in Australia that we compared different genotypes responses to EEF. I think there are some work done by Nicole at UQ and her team, looking at different genotypes responses to nitrogen or nitrogen use efficiency. I think they did find different genotypes have different nitrogen use efficiency. Some are more efficient than others.
Sorry, Alison, so if people want that information, it's under the nitrogen, more profit from nitrogen website on the CRDC. You can find that sub-project that looked at that and some of the results related to different genotypes and varieties and so on.
Thanks, Gus. I think there's 2 more. Did you trial delayed application of EEFs to better match N release with N uptake by the crop?
Thanks for the question. In our experiment, we didn't try different application times. Because we measured crop nitrogen uptake dynamics, we know in the first 2 months, roughly first 2 months, crop nitrogen uptake was very low, and quite often we have enough nitrogen in soil, and the soil nitrogen should be enough to meet the crop nitrogen demand in the first 1 month or even 2 months. So we recommend applying fertilizer application at least after 1 month after harvest, and somewhere between 1 month and 2 months would be perhaps more nitrogen efficient, because during this time the nitrogen uptake was not very high, and if you applied nitrogen really early, for example, in an extreme case soon after harvest, when the crops do not need much nitrogen, and there is the risk of nitrogen loss after high rainfall. That's a well, if for late harvested crop, and perhaps we got into the wet season very soon, and if you delay the nitrogen application by 2 months, for example, you won't be able to get into the ground anyway. So we don't have much option. We just have to apply the fertilizer shortly after harvest for the late harvested crops. So if possible, whether it's a normal urea or EF, we should delay the nitrogen application to at least 1 month after harvest.
All right, thank you. I think we might have to leave it there. It's getting on a little bit, but thank you to everyone for attending, and I hope that you found it valuable, and thanks for the great questions. Thanks, Dr. Wang, for obviously a very interesting presentation that raised, it's got a lot of interest from people. So we really appreciate your taking the time to present for us. I've put the link to the survey is in the chat. So, as I said earlier, it's very helpful for us to get your feedback. So if anyone can take 2 minutes to do that, it'd be much appreciated. There's also the link to the e-library, the final report on this SRA e-library. That link is in the chat. If anyone has any difficulties accessing any of those things, please feel free to get in contact with me. My details are on the website in the event information, which will stay there sort of for today. And the recording will be up in the next day or so. We've got another webinar planned for the 7th of October. The topic is screening for disease resistance and improved disease rating system. So there'll be some details about that in the next few days on our website, and then we'll send that out via the usual channels. I think that's it. Any other final messages, Gus?
No, nothing from me. Thanks to everyone for attending. Like I said, if you want more detail about this program, please do visit the More Profit from Nitrogen. I put a link on the chat there. Any outstanding questions, Wenjing, I'm sure you can answer those, and we can try to download the whole chat thing and put it on the website or something.
Yes.
So, yeah, thank you all.
Thank you very much, Alison and Gus. Just a quick thank you to everyone. And thanks for all the interesting questions as well. Perhaps I haven't got enough time to address all the questions. Please feel free to contact me either by email or give me a call. And I'm happy to answer any questions, particularly with the use of the decision tree. Thanks again.
Thanks, everyone. Have a lovely day. Bye-bye.
Bye.